Okay, in this lesson, what we're going to talk about is we're going to talk about ADCs in embedded systems. So ADC just stands for analog to digital conversion. That's all it is. The purpose you would use this for could be almost anything. It could be from reading voltages on a board to acquiring data. And what really defines the kind of work you're going to do is two things. The first is the rate at which you're going to capture information, whether you're going to capture it once a second, once every 5 seconds, which is super slow, or you're going to capture it thousands, hundreds of thousands, million times a second. If you're doing an oscilloscope, you're going to be doing it really often. I mean, super fast. Probably can't even do it in software. You probably require hardware to make a really good oscilloscope. But the point is, there's going to be a rate. The other thing that affects you is the resolution of your acquisition. So inside of most embedded chips, there is an A to D, sometimes 4 channels, maybe even more, maybe just a few. But there's always an A to D converter. And that converter could be 8 bits, could be 12 bits, could be 14 bits, but it's probably not going to be much more than that. And if you need more accuracy than that, then you're going to use an external A to D converter. We're not going to talk about A to D that is external to the processor, but just those that are in the processor themselves. So those typically are not going to be super high resolution. You'll probably get maybe 12 bits at the best out of them. That's what we're going to use for this video. We're going to use whatever is provided in the processor that we're playing with. So before we get into this, let's talk about how ADCs are used. ADCs, you don't just read them, you actually have to kick them off. And they go through a process of gathering data, and then they come up with a result. So there's several ways that you can work with an ADC. A lot of ways, but they actually boil down to probably about 3 ways of dealing with them. The one way is you can just pull them, where you kick them off. You do some register manipulation to kick them off, wait some period of time, which is all in the documentation, and then after that, read the result, and then you have your answer. But that burns up a lot of CPU, and it's not really ideal for almost all applications. So then the next step would be to use a timer. The timer will kick off the ADC read, and then later it would read the result. What typically happens is actually you initialize the whole system. You start the read so that a read takes place, and when the timer goes off, it reads the value and kicks it off again. So the next time the timer comes off, it can read the value and kick it off again. So you'll be doing that at a very rapid speed. The timer's not going to be like every second. It's going to be much, much faster. The other way to do this is through an interrupt, where a processor interrupt is tied to this process, so that an interrupt goes off. This is even deeper into the hardware than a timer is. This hardware interrupt goes off, you can read the result, kick off the next one, and go again. Now I know people are going to say, well, there's many other ways to do it, but to me, the reality is it's just a mixture of what I've already talked about. There is many ways to do it, but it's just a mix of those 3 combinations. So we're just going to do the first one, which is simply to kick off the value, wait some period of time, and then go off and read the result. Now, the difference of this is the delay. Typically, at this point that I've discussed things, we haven't talked about delaying. Delaying in software is not really easy. You could do a loop of no ops, but then you have to make it loop a certain number of times based on how fast the processor is. So every processor will be different. So you can like loop 40,000 times, you might loop 90,000 times, who knows, on a no-op instruction. So that's not really the best way to go. So what I'm going to do in this example is I'm going to introduce an operating system. I've worked with many operating systems over the years, from super expensive ones to free ones. And my viewpoint, and it is my viewpoint, is that you should just work with the simplest operating system you can in real time. If you have a need for some, high-end features like Ethernet, Wi-Fi, or something like that, you're probably getting in a situation where you need a better operating system than an RTOS. But there are some cases, Internet of Things might be cases where you would actually have a small operating system, TCP/IP stack, and some of all the network features that you need, so that you can wirelessly connect to the Wi-Fi inside of a house or whatever it is, and be able to send data out to the cloud. So you may have a situation where you need more capabilities than just a general simple RTOS. So anyways, in this example, I'm going to be using free RTOS. Free RTOS is free. You can actually use it in any of your applications, including commercial applications. You can look them up on the internet, freertos.org, really easy. They have their operating system on many platforms. And I really think the reason there is a free RTOS is because RTOSs have been very expensive in the past. I've actually been at a company where the company had paid over $200K for the RTOS, which sounds nutty, but that's what the game is sometimes. But anyways, in this case, and for things I'm going through here, we don't need a bunch of fancy features within the RTOS, or within the RTOS. And reality is, I can add those features based on my processor that I'm using. I can do all kinds of things, but we're not going to get to that yet. With regards to an ADC, what we're simply going to do is go over how do you read the ADC, how do you fire it off, how long do you wait, and then how do you read the result. There's a lot involved in that. It sounds very simple, but it's much more complex than you think it is. Okay, so let's talk about the changes that I'm doing so that I can, frankly, be lazy and read the kickoff and ADC acquisition, wait the period of time I need to, and then read the result. And the big deal in there is waiting. By enabling an operating system, and you can see here that I have enabled the free RTOS operating system in STM32Cube-MX, this tool. So I've enabled it. I've also gone to the ADC and enabled the first one, so the first in channel, channel 0. And the one other change that you have to do is, if you put in an operating system, you can't have the timer set to its normal time. It has to be set to a timer, and then it will automatically set that timer for you. And the reason it'll automatically set that is it knows, because there's an operating system, that it needs to have a 1 millisecond timer. So when I selected this timer, if I set systic, I'm going to have trouble. It's not going to work. So I come down here and set timer 1. And when I do, it's actually going to set everything up for me, so that in the RTOS, I have a 1 millisecond timer. And all RTOSs use a 1 millisecond timer because they keep track of time, right? So anyways, that's the only change that I've made in my project. I'm not going to show the generation of it. I've already done it. But I'll show you some things inside of that. Okay, now you can see that I have RTOS in my project. So there's plenty of files in here. If I go through here, there's going to be lots and lots of files in here. So we're not going to get into too much detail here. Just the fact that we have included FreeRTOS. Okay, so now let's do some debugging. Let's first start with the fact that we've tied ADC1, which is the first ADC channel. It's right here, ADC1, IN 0, and we can see that this is PA0. That's the pin on the processor. So we go to the processor manual. So this is the processor manual. We go to the processor manual. We go till we find PA0. I say PA1. Let's look at that again. PA0. Okay. PA0 is connected to, it's connected to a push button. Okay, well, we can still work with that. And I'm not trying to show you any perfect numbers. I'm going to just try to show you that it actually works. So I'm going to start with debugging. Let's get started at the very top here. So this is our main. We come in here. The code is all generated for us by that tool that I just showed you. We're going to init the GPIO. Here's where we're going to init the ADC. So it'll all be set up for us. And the nice thing is up here, you've already given us a handle to work for. Oops, sorry, wrong one. Handle to work for with the ADC. So we're ready to start using it. Now, since we're using an operating system, when you first generate code, if you don't put in a whole bunch of threads, or sorry, tasks, then you just get a default task. And here's the default task it's going to run. So we'll take a look at the code that I've added to the default task here at the bottom. Here we go. So basically, there's just a couple of things we need to do. One, we're going to do start. Is kicking off the ADC. The next thing is, we're going to wait for it to finish. So in other words, we're going to wait for the ADC to say that it's done. And then once we're done, then we're going to go ahead and read that variable. Okay. So let's run this once. Remember, it's connected to the button. I'm not going to touch the button the first time. Okay, we're going to run it. Stops at main. I'm just going to go resume because, I should make sure I have a breakpoint. Let's go down to our code, make sure we have a breakpoint. And we do. We have a breakpoint. So we just run. It started that task. This is the default task that it starts. Here's the start function, which is going to kick it off. And then we wait. And now we have a value. Exactly what was expected, 0, because it's not connected to anything. When I push the button down, my expectation is to get the largest value from the ADC, because it'll be pulled high, I believe, is going to be what it's going to happen. Okay, so I'm going to hold the button down this time. We're going to run it. It's going to take us to our start. Again, we'll resume. We're going to step F6 in this case. And the value we get is 4,095. So, can you guess what the range of the ADC is? Okay. What's your guess? Yeah, 4096. Power of 2, that would be 12 bits. That's completely what I would expect inside of a processor. They're not going to have more than 12 bits. It's expensive real estate to have more than 12 bits. So there you go. This is just the first way where you're just going to kick it off, wait. It's actually polling for a status and a register. This function here is actually going to poll for status in the register. It'll also check if you have the DMA programmed, so you can't make a mistake and it'll kick you out with an error. That's no good. And then after it sees that the ADC functionality has said, hey, I'm done, then it reads the value. And you saw in the first case 0, second case 495. So that's the full range of 496, which is 12 bits, fully what I expect. For me to give you any numbers in between, I'd have to hook up a potentiometer to a bunch of pins, and I don't want to do this at the time. The idea here is I've shown you what you need to do to read the ADC in the simplest form. To do it with more forms, it's going to take more videos to do that. So in the simplest form, this is just doing a start, polling, waiting for it to complete, and then reading it. Okay, not with a timer, not with DMA, not with an interrupt. Okay. Okay, so where do all these functions come from that I've been using? Pretty simply, they're generated for me by the STM CubeMX software. So that's where I got them from. So as soon as you generate some software, go ahead and take a look at all these drivers here, which drivers are essentially the glue that you're going to use for doing these parts. So now when let's see if this works. Yeah, so when I hover over it, then I'm able to look at the code. So this, as you can see, there's a large number of things that are done to start up the software. I mean, so you have to keep this in mind. It's important to keep in mind all the software that's behind the scenes. And the reason for that is if you're making a decision about whether or not to use DMA or to use an interrupt, just realize that, if you're using DMA, you may not get the performance out of it that you expect because, there's lots of software behind here. And this software is actually, I'm going to show you this one right here. And the reason for that is that, let's see if we can get value, pretty simple. Polling, yeah, I think this is it. So the polling is first going to say, hey, are you doing some sort of DMA transfers? Because if you are, then we shouldn't be doing polling. So there's some things that take place here, okay? But basically, once this polling is waiting, then we go through to this, and this one's at least pretty simple. So, it's just going to get from the register the value that you're asking for. Pretty simple. So keep in mind that when you use these functions, take a look at what's inside of them. Maybe spend some time learning about them, what they're doing, what they're trying to accomplish, because if you have a need for speed, you may have to make some homebrew functions for yourself that's not going to, call so many functions and do so many things. Taking a risk, because, this is all well-tested software. You're taking a risk doing that, but, if you have to get the speed that you need, you may have to get into some more detail. So this is just a very simple example. I hope this helps you, take a look at it, try it out yourself. Not a difficult thing, but you will have to spend some time, getting things running, getting things working. Yes, it's effort, but it is what we do in embedded systems. We do have to put some serious effort into creating the products that we create. Okay.